Hello folks, today it is paper 5 here. So I am attempting a question which was in the exam of one of the colleges that I teach, and what I found was they were very much worried at the beginning of the exam is because a certain factor here was something new. So it says that a student is investigating the oscillations of a mass attached to an arrangement of springs. So we have two springs here. Figure 2.1 shows a mass attached to two springs connected in a series arrangement here. The student determines the spring constant K for the arrangement of the springs. A stopwatch is used to measure the time T for 20 oscillations here. The measurement of T is repeated and the average period T is determined. So this is the average period T, time for one oscillation. The experiment is repeated for different arrangements and different number of springs. It is such that T and K are related by the equation T equal to 2 pi root of m by K, where m is the mass. So the first question is, a graph is plotted of T square on the y-axis against 1 by K on the x-axis. So determine expression for the gradient. So this requires that I have to have T square alone at the left side, and all others should be at the right side. So what I did was T squared equal to 2 pi square is 4 pi square, so this root will remove, and m by K. So since I need 1 by K separately, so I separate this 1 by K here, and what remained was 4 pi square m here. So T square represents y in the graph, 1 by K represents x as it has said, so the remaining thing should be the slope or gradient. So gradient is equal to 4 pi square m. So I have done it in a arrangement paper because if I start doing it here, it will take a very long time. So I thought it would be a better way. So I did it myself and explaining from the paper. So then I have the table here. Values of K, 1 by K, and the measurements of T are given in figure 2.2. So we have a table of K here, Newton per meter, 1 by K, meter per Newton. Time for 20 oscillations, 2 times here. Then we have directly the time period T, and then square of the time period. So the first is about K here. So 1 by K has been expressed in 2SF here. So 2SF, all of these things is 2SF. So the dp is different here, decimal place, is because they care for the 2SF. But in case of time, we have error here, we have error or uncertainty here. So that's why we have two data, one is 22.2 and one is 22.6. So we have to find the error in T, because it says that include the absolute uncertainties in T and T square. So that means there is error here also. So in order to find it, that what we first do is we have let me do for the first one. So we have T1 is equal to 22.2 seconds. T2 is equal to 22.6 seconds. So average T should be equal to T1 plus T2 by 2 equal to 22.2 plus 22.6, 6 by 2, that's equal to 22.4 seconds. Then I have this average T time period is equal to this T by 20, because these are were the times for 20 oscillations. So it should be 22.4 by 20. That will be equal to, let me use calculator. So even the small things need calculator. So 22.4 divided 20 is equal to 1.12 seconds. 1.12 seconds. So this is the time period. Now to find the error in the time period, first I need error in this T. So delta T should be equal to T max minus this average T, or I can say it is this average T minus this T minimum. So anything can work. So let me work this one. So it is a 22.6 minus 22.4 equal to 0.2 seconds. So therefore then delta of this T is equal to this delta T by 20 is 20 once again, because these are the quantities for 20 seconds, and I'm changing it to quantity for one oscillation. So equal to 0.2 by 20, that's equal to 0.01 seconds. So my delta t will be equal to 0.01. So since it is derived error here, I am using it in 2SF. So 1 and 2SF are allowed, but I am using 2 because I need precision in the graphs. So it is 0.010. So now this is 1.12. So the error is 0.010 and the quantity is 1.12. So the error starts at the second place after decimal, and this quantity ends at the second place after decimal. So we don't need to do anything, it works. Now what you need is t square. So what I have is t square is equal to square of this thing. T square is equal to square of this thing. So it's equal to 1.12 square equal to its real value is 1.2544 seconds, second square. Then I have error in t square. So error in t square should be equal to delta in t square should be equal to 2. So let's do like this: delta t square by t square is equal to 2 delta t by t, or I can say delta t square is equal to 2 t square delta t by t, t gone, so it's equal to 2t delta t. So when I apply this formula, I'll have 2 into t is equal to 1.12 into delta t was 0.010. So that's equal to 0.010. So it should be equal to 2 into 1.12 into 0.01 equal to, so it is 0.0224 second square. So when I use 2SF, it's only equal to 0.022. So now this is 0.022 and we have this quantity as 1.2544. So error starts from the second digit. So I must use this quantity up to till the second digit, and third four should be neglected. So it should be 1.25 plus minus 0.022. 0.022. So that's why I have used here 1.25 plus minus 0.022. So in a similar manner, I can fill up other things as well. So everywhere I have used 2 SF for the uncertainties or errors, and I have written the previous quantity or the first quantity till that digit from where the error starts. So I am writing those things till that digit from where the error starts. So this is the pattern here. So then I drew the graph. So the graph was pretty straight here, not much difficult. So I drew the graph, and the graph was a pretty straight line. So I used a ball pen here to make it look a little bit blacker. Then I drew error bars as well. So in case of error bars, what I can see is so the first thing had error of 0.022. The first thing had error of 0.022. So let me see here. From here to here it is 0.1. That gives me 10 divisions. So that means my 1 will be equal to 10 by 0.1, and 0.022 will be equal to 10 by 0.1 into 0.022. So what that will be equal to? So it is 10 divided 0.1 equal to into 0.022. So that becomes 2.2 divisions. 2.2 divisions up and 2.2 divisions down. So for this point, what I have done is, so it is from here, you can see from here, so it is from here to here it is 2, so it's a bit more than 2.22. So from here to here it is 2, a bit more, so it is 2.22. So 2.22 up and 2.22 down. So in a similar manner, I have done that for other things as well, and drew error bars. So let us notice that the error bars are, so one division, it has spread one division here, one division here. So almost every it's like this, one division here, one division here. So that's a standard norm that I follow. So then I drew the best fit. So best fit was in the midway of all of them, and I drew the worst fit. The worst fit extended from its top middle point, to its bottom middle point. I could also have drawn this bottom middle point of the top point with against the top middle point of the bottom, but this worked fine, so I drew this. So I used a triangle here. I used the triangle here, triangle which crossed both the lines, So from there I determined the gradient. So I first picked up the points which could be used x1, y1 and x2, y2. So I drew I got these gradients here, I wrote many SF. Then I found the difference, uncertainty. It was in many SF, by I changed it to 2SF, so 0.29. So once it is 0.29, the error starts from the first decimal, first place after decimal. So I have to write the quantity only up to first decimal place, only up to that quantity which is after first decimal place. So it is 9.4 plus minus 0.29. So not much of an issue. So now comes the last page. So in the last page I have to find several things. So one of the things is using your previous answers, determine a value for m. Determine a value for large M, and this large M is related to this gradient by means of this. So what we have done here is gradient equal to 4 pi square m. So that means I have copied the same thing here. Gradient is equal to 4 pi square large M. So m is equal to gradient by 4 pi square. So I use this thing, and when I did calculations, I used full value. I can't use the refined values because they are just for presentation, not for calculation. So I got this. So I just wrote this thing. So 0.238. So nothing is said here. So I wrote 3SF. Then I have to find the percent uncertainty. So this will be delta m by m. Delta m by m equal to small delta m. So from this equation I have, so delta m by m should be equal to delta m by m. Other quantities do not have errors, so I use the proper value here, full value of this delta m, and this delta m is from the previous page here, So this is delta small m, and this is the value of small m, real value, best value. It got me this, so I use 2SF 3.1. So it is 3.1%. Now in number E, the most difficult calculation here. So in number E, I have determined the spring constant K for an invisible spring is the same mass that would have a period of 2.50 plus minus 0.01. So here, let me erase the equation here. T squared equal to 4 pi square m into 1 by k, which was the equation given in the very beginning. So which I used it here. So 4 pi square m is the slope, m into 1 by k. So k should be equal to k goes here, t square goes here, m by t square. So m is the slope is this thing. Here it is 9.4176 divided t is equal to 2.50 square. It gives me this. Then I have to find the uncertainty also. So what I have done is the fractional uncertainty of k is equal to delta m by m plus 2 delta t by t, because it's square here. So I got this. Then delta k is equal to this, k goes to this side into k. I got this. So I used the 2SF here. It is 0.058. So once it is 0.058, now what happens is error is 0.058. My quantity is 1.5058, and so on. So error starts from the second place after decimal. So I have to write this quantity till second place after decimal. So I have to round it off all of these things here. So it should become, since it is 58 or 588, it becomes 1. So 1.51 plus minus 0.058. So that's not much of a difficult issue here. But what happened here was, it was mainly concerned with the mentioning of uncertainty. In previous cases, they used to have either percentage or certain formula here, certain formula, but here they did not give it like that. So we use the approach of the practicals to find the uncertainty and the errors, and that works pretty fine.